Okay, let's get started. So in this video, we will talk about policy gradients. So in the last lecture, the last video, we introduced why we actually want to use policy-based reinforcement learning in the first sense. And we have seen that we can actually use random search or augmented random search as algorithms to actually optimize a policy that is parameterized by some parameters theta. However, what we have also seen is that we did not really exploit the sequential structure of the problem, and we did not really do reinforcement learning in a sense. So in this lecture, what we will actually do is we will define a gradient of our policy that actually lets us optimize our policy directly to maximize the return that we can get out of the environment. So, as in the general reinforcement learning setting, assume that we have a state action sequence of a complete trajectory, and it considers of capital T steps with S capital T being a terminal state. So our trajectory actually consists of state actions and state actions. And as usual, we have the reward function R, that our ST80, which is actually the reward that we received after observing the state ST and performing an action AT. And we define the return of an episode tau as the discounted sum of the rewards that we actually see throughout this episode. This is actually what we also introduced from the beginning. And what we actually want to do in this lecture, what we actually want to do is we want to maximize the expected reward, meaning that we want to maximize the expected return of a trajectory tau that we sample following a policy pi that is parameterized by some parameters theta. And so actually meaning that the expected value is taken with respect to drawing trajectories tau under a policy pi theta. And so actually this actually makes the problem equivalent to finding the best parameters theta that give the best policy that maximize the expected reward. And we can actually use different approaches to optimize the given objective. We have seen some in the beginning where we actually had a random search method, but we can also use something like hill climbing or genetic algorithms, or actually neural networks. So in this sense, we will really tackle, or in this lecture onwards, we will really tackle the problem of defining a policy via neural networks, and we want to update our policy, and we want to parameterize the policy by a set of parameters theta that we want to update in order to maximize the expected total return that we see from sampling the trajectory. And the question is, how can we actually maximize this target? And while this seems like a difficult thing to do, which it is, of course, but let's start it step by step. So how can we actually maximize this target? How do we maximize? In general, we do gradient ascent. Now, suppose we would know how to calculate the gradient of the return with respect to the parameters. Then, if we could do this, we could define the gradient of the expected return of a trajectory tau with respect to the parameters. And if we would have this, we could actually apply, using a learning rate alpha, these as an update to our parameters in the direction of the gradient, which would then actually lead to bigger returns throughout the iterations. And this is actually also what we will be doing, and this exactly is here what we actually call the policy gradient, which is in literature often also defined something like this, which is basically the gradient of the objective function with respect to the parameters. So this is the policy gradient, and this lecture is actually about deriving and using the policy gradient to update our policy. Some digression first, how a gradient is defined, and giving also some notation in this sense. So in this setting, let J of theta be some policy objective function, and what we actually want to do is, or policy gradient algorithms actually want to do is, they want to search for a local maximum in our objective function by ascending the gradient of the policy with respect to the parameters theta. So actually the gradient of parameters is so we want to update we want to define an update of our parameters, which is actually some learning rate in the direction of the gradient of the parameters. So then if you do these update steps in the ascending steps, so think of this like here being the maximum, the local maximum, what we would actually do is we would apply small updates to our parameters so that we will actually reach the local maximum in here. So note that while we usually in machine learning talk about minimizing some objective function, so we make actually gradient descent. So what we do is here we want to maximize the expected return, which basically means that we do gradient ascent, which is just like switching the minus to a plus. Okay, and in this sense, if we want to do this, this is the policy gradient, meaning that it is the vector, in this case, of partial derivatives of our objective function with respect to all the parameters. And alpha is some sort of small step size parameter. So this is actually what we will be doing using the policy gradient. And if we define it like this, we can use any deep learning or machine learning framework and put this into optimizers such as RMS, prop, or atom. But we want to do an ascent step instead of a descent step because we want to maximize instead of minimizing error. Okay, so the question now is how can we actually derive the policy gradient, or how is the policy gradient actually defined? So how can we actually get the gradients? So what you see is what we want to actually estimate is this one. We want to define the gradient of the expectation if we sample trajectories tau under policy pi theta, and the expected return is the thing that we actually want to maximize. So we want to actually find the gradient with respect to the expected return. And the question is now how to estimate the gradient. So the first thing that we actually do is that we also have seen in the past when we optimized in the reinforcement learning setting, if we want to estimate something that's defined by an expectation over an expectation, what we usually do is we draw Monte Carlo estimates from the environment. So we sample a lot of taus using our policy, and if we do this using Monte Carlo estimation, we can actually estimate the gradient by defining the expectation as a sum in a sense. So what we would say is like the expectation of the trajectory of a policy pi of gt is nothing else than the probability of it's nothing else than drawing many trajectories from the environment, and that probability of drawing this trajectory times the return we actually have gotten in this trajectory. This is nothing else than the definition of an expectation. So from here, as a next step, what we would do is we would simply swap the sum and the integral and the gradient. So the sum and the gradient, which is something that you can do. So the sum of the gradients is nothing else than the gradient of the sums. By the way, at this point, this seems like the motivation behind this seems a little bit unclear, but we will end up at a formulation that is actually really easy to understand, and many of the things that we will actually see will be thrown away. So don't matter if you do not really get to the intuition after watching the video first, but maybe watching it twice or also going through the material and also through the references in here will help you a little bit capturing the intuition. So what we do here is we simply swap the gradient and the sum, which is something that you can easily do. And what you now do is you multiply by a constant. So in this sense, we just multiply and divide by the probability of the trajectory under the parameters of our policy theta, which sounds weird in the first sense, but what we now do is actually we apply the so-called score function trick. And so in this sense, so what you could easily do is you can say that this is actually how it is defined. You can define through this equation, and this actually leads you to the fact that you can define it as a logarithmic function in here. the question is, why do you do this? Actually, what you now have is, now we have an expectation under the current policy, which gives us a sample-based estimate. So you can actually work with this equally well. You will see in a minute why this is really nice to have this kind of formulation in a sense. And what we then do is we can also again throw out our probability of the trajectory under the parameters theta, and we can define the expectation again. And what you see here is nothing else than that the gradient of the expected return of a trajectory tau under policy pi is nothing else than the expected gradient of the log probability of a trajectory tau under theta times the actual return of this trajectory, which is something that we in the next step need to estimate in a sense. So what we see here is now is if we want to look at this more carefully, and this is actually what we want to estimate in order to apply our gradient ascent step. What you see is, I mean, this is something that we can actually draw from the environment. This is something we can see, but what's still open is this one. So if we want to estimate the gradient of our policy, what we still need is the probability of our trajectory tau given the parameters theta of our policy. So this is something that we still need to derive in here. And I mean, the probability of a trajectory tau under parameters theta is defined as the the trajectory is defined as the state action sequence that we have seen in the first slide in this lecture. And the full probability of a trajectory under theta is nothing else than the probability of starting at state S0 and then going all the states that we actually see with the actions that we actually took, multiplied together, times the probability that we actually selected, the actions that we actually selected by our policy pi. So this is actually how the probability of a trajectory tau under policy pi is defined. But some of you might also see that this could be problematic in practice, that we do something like this. Maybe think about what's the problem in here. Exactly, this is what we have seen. What we have seen also in previous lectures. We do not want something like this to be part of our optimization process, because actually what we see here is the dynamics of the environment, which is something that we just do not have. So while the probability of a path is the product of all the next states and actions under the dynamics model and the policy. And this is really problematic in practice. But before we actually say we cannot solve this, let's go home. What we actually now you maybe, you will, in a minute you will see why we did all the derivation in the beginning. We do not actually need the probability of the trajectory under the parameters. What we actually need is we need to estimate the log of that. So we actually need the log probability of a trajectory and not the probability itself. And what we actually do is, the gradient of the log probability. So actually let's put all this together in before we actually start being frustrated. So what we actually want to have is we want to calculate this. And if we now put this equation into the log prob equation in here, the grad log prob equation here, we have the gradient times the logarithm of this. If we apply a logarithm to this, this actually turns into a sum. So each of the multiplications turn into a sum, which leads us to end up in here. So we have the log of p of this one plus the sum of all the logs of the certain probability transitions and the policy. And what we now want to do is actually we want to take the gradient of this objective function with respect to theta. And now what you see is actually, this is quite convenient because now the dynamics model disappears as they simply do not have a theta in it. And at a point, I mean, if we want to derive this objective function with respect to theta, the dynamics model disappears as the dynamics doesn't encode a policy in it, of course. So if we want to if we want to do this, the dynamics model disappears, and we really end up doing this one. Meaning that the gradient of the log probability of a path is simply defined over the policy in here. This is simply defined over the actions that we took. So the dynamics model disappears, and we get an unbiased sample of the gradient of the probability of the distribution over the trajectories. Okay, so if we plug this one in, so this is actually what we ended up with 4 or 5 slides ago, 2 slides ago. And if we plug this in, we can estimate the gradient, the policy gradient, just using this equation. And I mean, we have gone through the derivation of all this, and the dynamic model disappears, and we're just looking at this one. And the question is, what's the intuition behind this gradient? Why is it looking like this? And I mean, maybe what you see in here is it's really simple. So imagine that you see actually. What you see is like, you can imagine that going to the right is something like the times, and you see different state sequences over time depending on the actions that you actually took. And what you actually want to do is, or what you actually do is, if you're actually optimizing, or if you're actually using this gradient to optimize your parameters, you would actually, depending on, so you would increase all the actions that you took on the states that you have took them, depending on the return that you got through taking them. So if you have a state action sequence, if you have an action sequence or state action sequence that actually leads to much G, so actually high G, much return, you will actually increase this sequence, all the parameters that actually have driven you to actually choose this action, you would increase them. If you have like lots of negative return, you would decrease all these states and actions. And if you're somewhere in the middle, you would also like, so if you have, in this case, you have 2 state action sequences, and you would like increase the probability of taking the actions in these states a lot. You would increase the probability of taking this action in these states. You would just increase them, and you would decrease the actions of the states and actions of the actions that you took in these states. So this is actually the motivation behind this policy gradient. So without actually knowing the dynamics, you want to increase the probabilities of actions that you took in certain states, depending on if they led to a good reward or to a bad reward. Yeah. So, and actually, how do you want to, I mean, this is still an expectation. How can you actually solve this and use this in a stochastic gradient descent fashion? As always, as this is an expectation, we can estimate it simply using a Monte Carlo sampling of the trajectories. So you take like number of tau with all different trajectories, to sample them from an environment, leading to the fact that you sample your gradients, and then you apply them using stochastic gradient descent. Yeah, so you can simply do this, and this leads to the fact that you, depending on how good your returns are, you would actually you would increase also the probability of taking these actions. So if they are leading to much more reward, you would increase them a lot. If they're leading to positive reward, you would increase them a bit. If G would be negative, you would even decrease them. In a sense, this means that you, if you have a reward process that always gets positive rewards, this means that you will be always increasing, implicitly meaning that other actions probabilities will decrease, because always action space probability densities are capped as at 1. So in many cases you will end up increasing everything, but you will increase certain actions much more than other actions, meaning that in a sense the not so good actions will be decreased implicitly. Okay, so this is actually how you could implement it. It's like you can implement this and you will see that this is working, but there might be one thing that looks a little bit weird in the first sense, because if you're actually optimizing, or if you're actually if you're actually making one action in a certain state more probable than it has been before, you will weight this ascending step depending on the return of the whole trajectory. And the question now is, why would, and if you remember how actually G was defined, I mean, the return of the episode is defined over the whole trajectory, so over the whole state action sequence. And if you want to increase the probability of an action at a later point in time, why would it be important to actually take into account the reward you have gotten earlier? Because actually this is out of scope for this action, because from here it only counts what's happening onwards. And this can be just reformulated. So actually, why would we use the return of the whole episode? It makes no sense. Let's just reformulate it, and reformulate it with the reward to go policy gradient, which just means that don't take the return of the whole episode as a weighting function for your gradient, but take the reward that you can expect afterwards, after have you taking the action. Actually, why can we actually do such a mathematical reformulation? So there's also an explanation for this. So actually, all the actions that you have taken before are, or the return or the reward that comes from the actions you have taken before, is conditionally independent of what's happening now. So meaning that you can actually treat everything that happens before as something like a baseline that actually will not change the expectation. So we will see this in a minute, but this is the very intuitive reason why you can do this. I think it's intuitively clear that to actually calculate the policy gradient at this point, it is not important what rewards you have seen in the past for other states and actions, because they are actually not counting what you're what you're doing now, to your optimal behavior that you're doing now. And one more thing to do on this. So this is like also a nice visualization of Andre Karpathy, where it also sees you like, why does the reward to go help? So if you see like limited experience of 4 trajectories in this case, and the question is, if you want to increase the probability of certain actions at certain states, what you will see is it doesn't make sense. So it doesn't make actual sense to see all these intermediate rewards and to actually, depending on your current state, to actually change things that happened before. You always consider the probability of the gradient should be like more tied to the updates or to the actual actions that happen afterwards to this, and not to what happened before, because they are actually not relevant anymore at this point in time, because there's different situations in the beginning. Okay, actually, how can you put all these abstract things into an algorithm? And the most simplistic algorithm at this point is called reinforce. Reinforce does exactly what we actually have introduced now in the previous slides. And the general idea of reinforce is that you update parameters of a policy using stochastic gradient descent. You use the policy gradient theorem, so you actually estimate the policy gradient like this, and you use the return to go, so actually which is actually the estimate of the Q function, as an unbiased sample of your return. I will tell you in a minute why it is an unbiased sample. We will also make some intuition around this, and maybe let's just go through the pseudocode shortly. So the input to your algorithm is a differentiable policy defined by some parameters theta, which in the easiest case could be a neural network. It could also be some smaller thing that you calculate analytically can calculate. Then you define a step size alpha. It's a small learning rate in a sense, and you initialize the policy parameters theta maybe to 0 or something. Like you just initialize your network, and what you will now do is then you loop forever or over episodes, and you generate a whole episode sequence starting from some initial state following your current policy until you reach a terminal state. And what you then do is then you start from the beginning of the episode until the end of the episode, and you calculate the reward to go in this setting. So this is now different from how we have seen the pseudocode in Monte Carlo policy evaluation, where we actually summed up the return from the back. In here we do it from the beginning, so we actually sum up we actually, for each of the state that we are actually now evaluating in our trajectory, we calculate the reward to go from this state onwards, and then we just update our policy parameters using the policy gradient theorem, meaning that we update the parameters a small step towards the reward to go, which is now in this case the discounted return at this point, in the direction of the gradient of the action in this setting. So this is the simple version. Put everything that we have seen in the last slide into an algorithm, and only a few lines of code you can do this. And what you now let's see maybe how reinforce actually works in practice. So this is an example from Satin and Barto's Introduction to Reinforcement Learning book, and you have a simple small environment. It's like very similar in a sense to what we have seen in the policy based RL intro video. You have a short corridor actually where you have a start state in here and a goal state in here, and it has a special cell in here where it is actually doing a switching operation. So it actually says whatever you take in, whatever action you actually want to take in this, I will actually reverse this action. So meaning that you actually need something like a stochastic policy to actually solve it after all. Some other background information on this environment. So as usual, you get a -1 reward per step, which actually means that you want to actually solve the grid world as fast as possible. In each of these states, you can only take 2 actions, either go left or right, and they have usual consequences to either go left or right, except in this one, because there they are reversed, and all the states appear identical, like also what we have seen in the beginning. So being the problem that we have the aliased grid world example. And then we also define a greedy policy and an epsilon greedy policy with epsilon parameters in here, meaning that you can a little bit trade off the action of going left or right with a certain random probability to actually solve it in practice. And you see that with this kind of combination where you actually come up with epsilon greedy left and epsilon greedy right policy, and what you can actually achieve if you use an optimal stochastic policy, which actually can be trained in a sense in the end to actually reach the optimal, which in the end is the actual optimal policy that you can actually estimate from the environment. So what you see here is actually different step size parameters alpha and training reinforce on this short corridor grid world. So feel free actually to also implement it. I mean, reinforce is implemented fairly quickly because it's not that much. If you use PyTorch, you can like implement it in like maybe even less than 10 lines of code. And even the short corridor example is like implementable really quickly. And what you see here is the achievable reward, or you see actually the value function that actually is actually approximated to the value of 0.1, which is actually the start state of reinforce when you train the agent over several episodes. And what you see here is with a good parameter of your step size alpha of 2 to the power of -13 in here, you can get up and reach the optimal policy fairly quickly, while with smaller learning rates, you will actually end up taking much longer to actually reach the goal. Summing up, what is the simple policy gradient algorithm? So when we talk about policy gradients and also what we have seen so far, we defined on policy, policy gradient algorithms that we have seen so far are in a sense on policy algorithms, because we actually follow the policy we are currently evaluating and optimizing, and they work with continuous as well as discrete state spaces. They are actually working better for continuous state spaces after all, and the basic framework is always the same. So we initialize a policy network randomly, and then in an infinite loop, so we repeat forever, we collect a bunch of rollouts given that policy in order to actually estimate our gradient. And then what we actually want to do is we increase the probability of actions that we have seen in our samples that we've drawn that actually worked well. And we optimize them, and then in the end we actually hope that everything works as it is supposed to. As summary, what you have also hopefully seen is that they are good and easy to follow. So what you actually see is that they are intuitive algorithms. So they are only using a few lines of code. You cannot do much wrong with them. In order to actually, if you compare that with value-based reinforcement learning algorithms, what you see is that they are really tricky to be stabilized. And what you see here is like you can come up with an algorithm that works fairly well, even if you just invested a few minutes or hours in implementing them. There is also good and easy to follow implementations available. You will see here a bunch of frameworks and algorithms you can refer to. They are also easy to parallelize, so actually you can collect experience samples using parallelized steps. Then you can estimate the gradient, just do an update. This is like a very easy thing to do. On the downside, what's maybe not intuitively clear right now is that we actually have a high variance in the estimation of our gradients. So as we actually do Monte Carlo samples of the environment, we actually see a lot of noise in the things that we estimate. So actually they are prone to variations. So actually we run our policy and we see different variations of returns, meaning that we see high variance targets in our rollouts, which is something that we will deal a lot with in the upcoming slides. So variance is one thing that is really critical for policy gradient algorithms. So actually they have no bias right now, because we actually estimate the gradient bias free, because we actually use samples that we extracted from the environment, but they are high variance targets. And because of this, they are in their form not capable of solving modern continuous action control problems because of these variance issues, most likely. Okay, so what do we want to do right now? So a basic thing that we also have touched a little bit in the value-based reinforcement learning algorithms, what we actually want to do is we want to hide the variance. The question now is, how could we actually hide the variance? In a sense, we already did this. We already hid some kind of variance as we introduced the reward to go instead of the total return of the episode. What we have seen there is actually, or what we hopefully intuitively have understood until there, is that while the reward to go actually is different from the return of the episode, cutting off everything that happened before a certain state, on average, is bias free actually. So actually everything that happens before has actually no influence of what happens afterwards. It has no influence on how we actually should change our policy at that point. Meaning that while the reward to go and the total reward of the total return of the episode are different, if you collect a lot of trajectories and you consider all of the rewards to go from a certain state, everything that happens before averages out to 0 and will be 0. And this is actually something that we can do. We actually still remain bias free, but we take out variance out of our estimation. So in this sense, meaning that we need much less examples to actually get a low variance estimate of our gradient for a certain state. And there is also a little more formal or mathematical understanding why actually introducing such certain family of functions that we actually subtract from the reward to go in this sense are actually operations that are bias free and take out variance. There's actually a certain family of definitions and baseline functions that we can use that are actually allowed to be used in this setting. And before we actually get an understanding of this, I will show you why this is the case. And for this, actually, consider that p theta is a parameterized probability distribution over some variable x, some random variable x. What we then see is, you can prove this is available out there. So if you take the gradient over estimates of samples from your probability distribution, this gradient will be 0. I think this is intuitively clear. And however, from this follows also something that is really interesting for our problem at hand that we are dealing with. Because this means that from this, we can follow that for any function b that only depends on the states and not on the actions, because we actually want to increase the probability of actions. If we find a function b that only depends on the actions and not on this, depends on the states and not on the actions, we can simply subtract them from our system. And this is because the following. So actually, if we take the expectation over actions that we draw from our trajectory tau, policy pi, which is what we do, then the gradient so the policy gradient times our baseline that depends on st is 0. And if this is the case, we can subtract or add such functions as we want to our expectations. And this is 0 because of the following. So we can actually reformulate this as the expectation over, so actually we in this sense already would do it again. We take in the sum of the expectation, and we put this in, imply an inverse score function trick. And this is actually the same as we did it in the policy gradient derivation in the beginning of this lecture. And then we take here the definition, so we end up with this term, so we put everything out, we end up with this sum, and this sum is actually taking up for all the actions that we have, the probability of taking this action in this state for all the actions. This by definition sums up to 1 because it is a probability distribution, meaning that we end up with function b times the gradient with respect of theta of 1, which is actually 0. So this is 0, so meaning that we can subtract or add any function, any baseline function b to our policy gradient if b only depends on states and not on the actions. This has no influence on the sample mean of our samples actually, but helps to reduce the variance by adding or subtracting a constant. The intuition behind, which you can also use maybe to think about it, is you will push the preferences. So actually you can subtract variance out of your estimation, and what you actually came up with this is, or how you can also think about it, you want to push preferences if they are larger than expected, or you want to pull preferences if they are lower than expected. So this is maybe the intuition behind this. So yeah, as I already said, this allows us to add or subtract any of such terms, we call this baseline functions, to our policy gradient without changing its expectation actually. So if you do it like this, we would just subtract some baseline functions from our return in here, ending up with this one. We also did this, by the way, as we used the reward to go hypothesis instead of the full return of the episode, given that B does not depend on the action. Yeah, so actually I think this is maybe a duplicate. So actually what's the intuition behind this? We have seen this so far, and we do not want to estimate the gradient in certain areas with variance we introduce through parts of the trajectory that are not important. So if we estimate the gradient at this step in here, it doesn't matter which of the rewards we got from the beginning in here. And what we also want to do is we want to not estimate the absolute value of the gradient. We want to estimate if it's better than expected or worse than expected. And this also gives us a viable training signal for our gradient. One further thing to mention, which I also maybe touched a little bit, mostly in practice you will keep on increasing everything because you either have a positive or a negative reward, so we actually will always increase everything, but you will increase some more than others in a sense. And yeah, in order to estimate the gradient perfectly, in order to estimate which trajectory or which actions to actually push more than others, you require a lot of samples to actually average out the variance from the estimation targets. And actually you want to increase or decrease the probability of a path if they are better or worse as the average you would expect from this one. I'm talking about better or worse than expected, because this is actually something that really takes out variance a lot from our gradient estimation, and I will have maybe a more intuitive example in here. So we have seen that we can introduce any baseline to our targets if it's not depending on the action. And what we also have seen in DQNs is the usage of advantage functions. So we had this regression head in the end where we actually not predicted the Q targets, the Q values of each of the actions, because they are actually large values and they only differ a little bit from each other. We actually defined the advantage function that says we want to predict the value, and for each of the actions that we can take, we want to predict the advantage of this action over the value that we have seen in the state. So we want to actually see how much better or how much worse this action is towards the value of the current state. And this is something that we want to also apply to policy-based reinforcement learning as well. And this is also something that we will apply in here, because the baseline functions actually allow us to do exactly this. The intuition behind this is that we actually want to see, so if in a certain state and we push a certain action, and if an action sees what it actually expected, it feels neutral about it. So actually it didn't want to change so much. But however, if he sees that actually it is much better to take one action over the other, he wants to actually really push this action much more. We always did this in the reward to go variant, and what we will be doing, and what also I introduced with the DQN example in the previous lecture on value function approximation, we introduced the so-called advantage function. And the advantage function is nothing else than that the advantage of a state of an action AT in a state ST is nothing else than the Q value of the state minus the value of the state itself. This actually pushes all the action in a certain state to a lower value, because it only actually considers the advantage of one action over the other actions in a sense, or over the value of the state. This leads to a faster and much more stable policy learning. There is also maybe a more intuitive example in this, and the question is to you, also what helps our agent to learn faster in a sense? Is it helping information about invariant actions on good states, which is actually what you see here? So just consider that in invariant actions on good states, or information about good actions in bad states. What you see here is on the left side you see a bad state that has a value of 10, and on the right side you see a good state having a value of 100. You also see this a little bit maybe that the pole is slightly off in this case, and here it is balanced quite well. And what you see here is you see, like in this case, you see a large Q value in this sense, yeah. And however, while the Q value is large, it would lead to a large policy gradient update in a sense, because you actually get a large return out of it. However, you already have a large return, so your state value is already very large. So if you would use the Q function to update your policy at this point, you would like increase a lot. However, if you consider the advantage of your action in this sense, it's not that big. So you actually do not need to change so much. So you do not want to push the action too much, because actually taking this action is not that important. You could also take another action. So in this sense, actually, the Q function is much, much smaller in general, because it's only 50. However, taking the right action in this sense is much, much better than the state value you're currently in. So if you now take the advantage instead of the Q function itself, it is 40, while it is 0 in here. And this somehow normalizes how you push and pull the certain actions on your policy, taking out all the variants, but taking as an example what you're really caring about. So you wanna see an advantage of 40 taking action right in the state, and which means that you really want to push action right in the state, while you do not really need to push action do nothing in the state. You can easily put this also in, so the general definition of using baseline functions to estimate, to actually steer the policy gradient, you can easily put into the reinforce algorithm that we introduced before, and it's not changing that much. So we have as an input differentiable policy parameters, pi. What you also have an input is a state value function parameterization. So actually what you would do is here, in order to actually take the advantage, or actually to calculate the advantage at this point, what you also need to do is you need to calculate the value function of a certain state, and Q is the sample estimate that you actually see from the environment. So you actually can calculate over the sample the Q value of this sample, and you subtract the value estimate of your state, which is actually giving you your baseline. In this case, it is a state value function in a sense, but you really can calculate it using usual gradient descent, stochastic gradient descent, without all the bootstrapping issue that we usually see in reinforcement learning. So you can just use your data over your samples and use it to train parameters W to actually estimate a value function from it. You have step sizes for your policy and for your value function, and you start over again with your policy parameters and initial state values. You keep generating an episode, and now for each of the episode, you calculate the reward to go in this episode. This is something that you'll still be doing. And you calculate the, for each of these rewards to go, you actually calculate the advantage, which is nothing else than the reward to go from a state onwards, minus the value you already have, the estimate of the value you already have for the state. And then you apply a one-step TD arrow update to update your value function, and the policy gradient update as you have seen before. So this is really working well. It takes out a lot of noise, a lot of variance actually for your targets. However, it introduces a little bias because you actually now estimate a value function in here. However, as you have seen also in previous lectures, this usually helps a lot in actually converging to the correct values and also to the correct policy in this case. So you're now interested in the policy, so this helps a lot like this too. So in this sense, you see the same example of the reinforce algorithm that actually had the best parameters in the short corridor example on the previous slides, which was 2 to the power of minus 13. And this was the best performing variant. And what you see here is if you take all the variants out, so if you use the reward to go plus the estimate of the value of the state in order to actually come up with the advantage of the action in a state, you come to the, or you actually reach, you plateau to the really correct policy, to the really optimal policy much more much faster, with much less experience you need to sample from the environment. You can also plug this in an algorithm that we used to call the vanilla policy gradient algorithm. This is also what you will be implementing in the exercises, and it's like it's also a framework that you can also reuse if we start on implementing and getting onto new ideas. You can really plug them into this framework and keep on iterating on it. And it is always like the same thing that you will see also in all the other policy gradient algorithms. In the beginning, you collect a bunch of trajectories by running your current policy. You compute the rewards to go, RT, and from them, and together with your current value function, you compute the advantage estimates. So this is actually what you want to optimize towards. With them, you actually compute the policy. So sorry, it's a little bit shifted. From this, you actually estimate the policy gradient. So you actually the logarithm of your policy, of your action, of the states, times the advantage in this case. And then from this, you can just compute the policy update, which is nothing else than the current policy plus some learning, plus some small step parameter times the gradient via some gradient ascent algorithm, just like such as Adam or stochastic gradient descent. And if you do this, in order to actually estimate the advantages fairly well, you need to update your value function. And this is usually being done through some value function fitting, could be a neural network or something else. In this case, it's really just a regression target that minimizes the mean squared error between what you have seen through your samples and what your value function is predicting. And you can do this via some gradient descent algorithm. Yeah, so problems still with this or limitations of this. The learning rate in here, which you use to actually update your policy, is a heuristic that is not easily be tunable, because actually your policy is deciding on the data that you actually will see in the future and that we will use to actually estimate the value function, also to actually collect data. And if you move too far away from what you know, that's good. So if you take large gradient steps on your policy, you will probably see completely different things on the environment. It might also be the case that you cannot actually recover from that. But we will also tackle this explicitly with an algorithm called trust region policy optimization, where you define really like a trust region over your policy, which defines the safe update step of your policy with respect to your parameters. Okay, this is it with the general policy gradient framework. One final thing to mention, which is not really explicitly been done here in this lecture, is the thing with exploration and exploitation in policy gradient. What we see is that with policy gradients, we train a stochastic policy in an on-policy way. So we collect data using a current policy, and then we update the policy parameters with the policy gradient that we estimated from that experience. And meaning that the actions that we sample are according to the latest version, and also meaning that we implicitly have a randomness in the selected actions, because we initially have some initialization of our policy from which we sample from, which implicitly becomes also less over the course of training, because we get more information and we keep on increasing actions, which meaning that our probability distributions become sharper. Actually, and this is because the update rule actually encourages to exploit the rewards implicitly. However, through sampling, we still keep on taking actions that we have not investigated so much. And because of this also may result in local optima if we keep on doing the gradient updates too far. So if we have a large gradient update and we see an action once or twice that has been performing very well, we really increase this action in this state a lot, meaning that we will never explore again other actions in this state because the probability distribution becomes so sharp. And this may result in local optima, that is from which we can hardly recover if we go on through the iterations. This is some further references that you can actually use to look into. And in the next video, we will talk about octocritic algorithms that help us to trade bias and variance in the reinforcement learning setting.